of course, is from natural languages. You know what a natural language is? If you understand what a natural language is, you should be able to get into the definition of a formal language fairly easily. So to that end, we need to start defining some things. In terms of a language, then, so a formal language, but in terms of a language, what is the most fundamental unit of a formal of a language? You know, what are languages built out of? And you might, well, let's just start with that. What is the most fundamental piece of a language?
Yeah. Character?
Yeah, character isn't bad. Yeah, okay, so I like that word better, so we'll just go straight there. So a symbol. So languages are built out of symbols. Character is a fine word too, but I prefer symbol just because it's so. Because when you think about characters, a lot of times, well, what are some symbols? Symbols, you know, are like lowercase letters, you know, of course, and uppercase letters, but also digits. You know, and special symbols. Oops, that's not a special symbol. So on. So, you know, these are all symbols. Some of them we may refer to as characters or not, but that doesn't matter. But so indeed, that's the fundamental piece of a language, right? To talk about a language, you have to talk about the symbols, which is worth mentioning now, by the way. So what we're going to do is we're going to put the symbols together to build up a language. So there's sort of two parts of a language, right? There's the syntax and the semantics. The syntax just talks about what the things look like, what kinds of things are in the languages, and the semantics is what these things mean. We will never talk about the semantics in this class, okay? So formal languages, for us, languages, we're just interested in what's there. What kinds of things are in the languages, what do they look like, how do they get there, how do we know if they're there, something like that. So this class is all about syntax. So we're just interested in putting symbols together and trying to figure out how they combine, not what they mean. Okay, so symbols. So we don't usually use, English, for example, I don't think uses all these symbols. Right? It typically just uses the symbols in the first two lines, right? So we have a word for the collection of symbols that pertain to the language in question. Just dragging vocabulary out of you. So what is the word for the collection of symbols of interest in terms of a particular language? Yeah, that's not bad, but I like someone's better because we will use that, and that's alphabet. So the alphabet is the set of symbols pertaining to the particular language we happen to be talking about. So, for example, like I said, the first two rows correspond to the alphabet, that you usually use like in a natural language. Maybe if we're just talking about, machine computers, then the alphabet is going to be zeros and ones, right? So because computers are all binary. So the language of computers, the alphabet would be zeros and ones or something like that. We tend to be general, so we have a symbol we use when we talk about an alphabet. Sometimes I want to say, okay, we've got an alphabet. I don't want to tell you what it is. I just want to say that there's an alphabet. So when I do that, I use this symbol, as does the book. The sigma symbol denotes an alphabet. So for example, you might say, if we're talking about English, we might say sigma is A, B, C, right? A, B, whatever. So in this case, I'm saying the alphabet is this set of symbols, right? So the point of this statement is, if you see sigma on the board, and barring any other, situation, I'm talking about an alphabet. I'm talking about a set of symbols. Of course, you've seen sigma in other places too, right? Where else do you see sigma? summation, right? So it's an overloaded symbol, but that's what it usually means here. If I don't say otherwise, since this is formal languages, well, let me ask you this. Since we're talking about formal languages, we're going to be more abstract. So, we don't have to necessarily be so general to talk about all the different kinds of languages. We just want to be able to talk about enough complexities to sort of cover all the situations. How big of an alphabet do you need to be interesting is what I'm trying to ask. Do we need 52 letters, or do we need 26 symbols? Or is one symbol enough, or do we really not need any? What would sort of be the fundamental size of an alphabet that would allow us to be interesting, if you were to guess?
2.
2. Why 2?
If you only have 1, there's not enough. You can't really tell us where.
Yeah, no, you're exactly right. I agree. For an alphabet to be interesting, 2 is kind of just the right number. An alphabet of size 1, if you had an alphabet and the only symbol is A, then you can write A and AA, and there's strings of A's. It doesn't look very interesting, right? But to be interesting, you need more than 1, but you don't want too many to be unnecessarily complicated. So if I don't say otherwise, and the book is the same way, if I don't say otherwise, and I'm talking about an alphabet, the alphabet is 80. Okay. Again, it's sort of in the spirit of computer science. It would be almost nicer to use 0 and 1 in sort of the digital spirit of things. But 0 and 1, you can't help sometimes but trying to interpret them as numbers and things, and it gets a little confusing. So instead of 0 and 1, we usually use A and B. So if I don't say otherwise, and I'm talking about a language, then the alphabet is A and B. Those are the symbols we're going to be using. Okay, we'll keep working our way up. Okay, what do we do with these symbols? How does a language use symbols? I'm trying to eventually build up to what the definition of a language is, right? So eventually we're going to say a language is something.
We make words.
We make words, right? So that's the next step. So using an alphabet, we build words. Again, as I use the word words. And interchangeably, and again in the spirit of computer science, there's another word we use instead of word.
Strings.
Strings, right. So we can have words, we can have strings, whatever they are. It's a, so what's an example of some words, So AB, I like that one. Or AB, right? These are all fine words. Okay. So a word is just a string. Is it a set of symbols? Well, that was a yes or no question. Is it a set of symbols?
Yes.
It's a subset.
Yes.
Yeah, I saw you were shaking no. Why not?
Because you have duplication.
Yeah, you have duplication, right? So that's one reason. Sets never have duplicates. If this were really a set, the set A would be the same as the set A, right? So it's not a set. But even here, there's a reason why this doesn't really look like a set, yeah? Because order matters, right? And with a set, order doesn't matter. So these are definitely not sets. So sequences is probably as good a word as any. So the order matters. We're putting the symbols together to form strings in order. They're not sets yet. Okay, so we know what symbols are. We know what the alphabet is. Oh, so we know what words are. Yeah, I guess that's okay. Okay, so we know what words are. Are we ready? Yeah. We went faster than I thought. So what is a language? Combination of symbols. I mean, think about the English language. What is the fundamental? Ignoring meaning. What comprises the English language? What is a language? Yeah, that's exactly what it is. A language is just a set, and in this case, some reason I usually say string, if I'm not sure why. But language is a set of strings. It's a set of words. That's what a language is. We don't care how they get put together. We don't care what they mean. What we're interested in is the set that comprises them. Okay? So I'm for example, so language 1 might just be A, B, and B. That's a perfectly good language, right? It's a set of strings. Very often, languages, the set is something we can sort of describe in English, right? It is a set of strings, but sometimes it's easier to define in English. So for example, if I were to write, say, this set of strings, is the pattern clear? What set of strings is L2? What language am I talking about there?
Perhaps all combinations that start with an
Yeah, I don't know where combinations comes from, but it's the set of all strings, right? So that's what I'm trying to denote here, right? So this is just the set of strings that begin with A. That's a perfectly good language. It's just a set of strings. Any set of strings is a language. So this is a set of strings. This is a set of strings, right? All are fine. Well, let's do a couple others. So again, in the spirits of sets, you can imagine something like this. So I don't think I can even ask a question here. It's fairly obvious what language this is, right? Well, no, maybe I can ask a question. Oh, actually, yeah, there's a couple interesting questions. Give me some strings in this language. BB is not in this language. AABB, right? And I guess I've actually snuck in some notation here that maybe wasn't immediately obvious. The notation I snuck in is, if I say something like, so, that's what today is going to be all about, getting the notation down. So if I write something like A4, what do I mean? Yeah, I mean 4 A's, right? So that's what this means. So what am I saying here? So, like someone said, AABB is in this language, yeah?
Any string that starts with A's and ends with B's.
And the number of A's and B's equal.
And the number of A's and B's are the same, because N, right? So it's the same N. Yes?
Empty string? Because you...
Empty string. What's the empty string?
There's nothing on the language.
Yeah, I agree. You're getting way ahead of. I was going to drag that out of you. Are you getting this from 256?
No, I'm retaking.
Oh, I see. So you're cheating. Okay, but you're absolutely right. So maybe it's time to hop over there. Okay, let's get some more notation out of the way. And then we can talk about your empty string, and then we can talk about that in this context too. You're right. Okay, let's talk about some notation. So, what is this? If this was a quiz question, what would you write? Okay, hang on.
Are those like absolute bars, or are they?
Yeah, they're exactly like absolute bars. So, and in some sense, that's part of the question. When you write absolute bars, in general, what do these bars usually denote in a more general sense? In one word, anytime you put this around something, what are you denoting? In general. And there's a good one-word answer.
Magnitude?
That's even a better one word. Nah, it's not as good as my word, but that's the spirit, right? I'm thinking more like size. Anytime you put this around something, you're kind of talking about the size.
Cardinality?
No, it's even worse. Because this is a string, and talking about the cardinality of a string doesn't make much sense. But if you're talking about the size of a string, so it changes depending on what you're putting it around. So if I put these bars around the string, what do I usually mean by the size?
Number of symbols.
Yeah. And what's the one-word answer?
Length.
Length, right? In that case, it's the length, right? So the size of a string is the length. So this would be 3, right? And so similarly, the size of the string with just A is going to be 1. And so now a lot of you were way ahead of me, but that's okay. Some of you are saying then you can have a string of length 0. But of course, I guess as computer scientists, that doesn't bother you, right? You've programmed strings of length 0. In fact, someone in the last class, maybe you'll give me the same answer since I'm talking about programming. So the string of length 0 is a perfectly good string. Among all the different words or strings we can talk about, there's the one of length 0. The question is, how are we going to denote it? There it is, right? The string of length 0. Well, how do you know it's there, right? We need a symbol for the empty string. So how are we going to write it down? Yeah? No. Oh, null meaning this? No, that's taken. Because what is this usually used for?
The empty set.
Empty set, right? Or you do sometimes say the null set, but this is usually used in the world of sets and not in the world of strings. So, we have to sort of be consistent with our type.
The little epsilon?
So as a programmer, we're not going to use it, but I thought it was a great answer. So, you're going to be the victim of things from the last section. As a programmer, how do you write it? Yeah?
Oh,
The 2 quotation marks?
Yeah, right? As a programmer, you write this, right? So that would be, that in some ways, that would be a very natural way to write an empty string. But that's 2 symbols, and it's harder to write and stuff like that. So what did someone else say?
It's lambda.
That's another one. Well, here's something else
The
first.
epsilon?
Yeah, so sometimes you see epsilon, or sometimes you see this epsilon, sometimes you see lambda, and sometimes you see capital lambda. So all 4 of those appear depending on where you're reading. Who said epsilon, and where did they see that?
I haven't seen it used in that context, but I just figured because it looks like a little E.
Oh, no, it's a good guess, and it is very common, and it shows. I believe it's written that way in the book I used for 256. Does that sound right? That was a long time ago for most of you. Okay, anyway, this is what I'll use. So anytime I'm talking about the empty string, I'll write the lowercase lambda. Anytime the book talks about the empty string, it's going to write the uppercase lambda. Okay. So, like I said, I generally try to follow the book very carefully, but there will be exceptions. And here's one. But lambda's lambda, so it's not so bad. So lambda's a perfectly good string. It's the empty string, like we said, or we haven't said yet. So therefore, what is the length of lambda? 0. Right. Well, I guess as long as we're talking about vertical bars, yeah, as long as we're, okay, as long as we're talking about vertical bars, what is this?
That's the cardinality.
What's the size? Right, so, the size of a string is the length. What is the size of a set? The cardinality, right? And in a few more words, what is the cardinality of a set? Okay, hang on. Of a set in general, what is the cardinality of a set? The size, yeah.
Number of elements.
the number of elements, right? You know, a set is a collection of elements. So the cardinality of a set is the number of elements, right? So this is going to be 2. And so, well, since we brought it up over here, what's the cardinality of the empty set?
There's a paradox, isn't it?
Nope.
No, 0.
How many elements are in the empty set?
1.
Okay, the empty set is a set,
Yeah.
but how many things, and see,
1.
we have to, so,
Say it's a paradox.
It's popping off.
so we have to decide, you know, what we're counting, right? You know, so this is the size of something. So we're not talking about how many sets we're talking about, because if this is a set, how many sets are we talking about? We're talking about one set, right? This is a set, this is a set. So if the answer were 1 in this case, the answer would always be 1, right? Put the vertical bars around the set, and there it is, and it's 1. So that doesn't make as much sense as trying to count how many elements are inside the set. So how many elements are in the empty set?
0.
0. There's nothing in there, right? So it's 0. Well, let's see. Here's another language while we're at it. It's perfectly good language, right? It just has 1 string in it. And just to make sure you're with me here, so what is that? 1. Yeah. What is the cardinality of that set? There is one thing in that set. It's something that has length 0, but that's irrelevant, right? How many strings are in that language? And there's 1 string in that language. And I guess finally, I recognize a lot of faces, but I forget what class I had you in. How many of you did I have? How many of you were in my 256 class? Okay, no one. Okay, that's actually good. So you're not going to be biased here. What's the answer here?
Aleph null.
That sounds way. What's the simple answer?
Infinity.
Yeah, it's infinite, right? So indeed, if you write infinite, that's a perfectly good answer. But someone implied that you can be more precise. Aleph null, was that the word I heard? What does that mean?
The cardinality of the infinite set.
Oh.
There's a better word, right? So there are actually many different kinds of infinities, right? So like, you know, the number of integers is different than the number of reals. And the number of reals is different than the number of subsets of reals. So there's a lot of different infinities out there here. So Aleph null, yeah, that's more of a cardinality, but it doesn't describe it. Which infinity is this? Let me put it this way. There's a nice adjective you can put in front of this.
It's countable.
Countably infinite, right? So it's countably infinite. Basically, every infinity we're going to run into in this class, except maybe the last week, is going to be countably infinite. So, you know, infinite is infinite as far as we're concerned. Just writing infinite here is fine. The word countably infinite comes from the fact it's the number of integers, right? Or even more so, the number of positive integers. So how many positive integers are there? Well, there's 1, and there's 2, and there's 3, and there's 4, right? So what are those numbers? Those are the counting numbers. You're counting. So if it's countably infinite, that means you can count them. That means you can list them. So that's just where that comes from, but that's not going to come up an awful lot. When we were talking about L3 then, we were talking a little bit about, so we all agreed then, for example, that something like A, B, B, B is in L3, right? And then what started all this is, what did we decide the smallest string in L3 was? Right, but a little more briefly, lambda, right? Yeah. So lambda is also in L3. That's the smallest string. How do you know lambda is in L3?
Because that's when n is equal to 0.
Right. When n equals 0, right? When n equals 0, it's no a's followed by no b's. So that's exactly what lambda is. That's what the empty string is. Okay. Okay. So we got some more notation and terminology, I guess. Oh. Yeah, some more notation. When we're talking about strings, we also talk about strings abstractly. You know, I want to, like when we talk about integers, and we want to say, okay, given an integer, usually use a letter like I or J or something like that to talk about an integer, right? Or if you're doing the summation, right, sum I equals 1 to n, right? So the convention is that integers are usually, you know, like I and J or something like that. We want variables for for strings too. What's the conventional variable for a string?
W.
That's 1. Any lowercase letter near the end of the alphabet. So if you see a lowercase letter near the end of the alphabet, in this class you can be pretty sure I'm talking about a string. So, you know, I might say something like W and then, you know, equals ABA, or X equals BBAB, right? So lowercase letters near the end of the alphabet will usually denote a string. You can put strings together, all right? So I can put W next to X and get, and I wrote these too long, I guess, A, B, A, B, B, A, B, all right? What did I just do? What verb applies here? Concatenate. You can concatenate strings. If I concatenate two strings, you're basically just putting them next to each other, right? So I concatenated W with X and got that string. There's some overloading going on here because a symbol is also a string, right? And so the context will tell you whether you're talking about a symbol or whether you're talking about a string, and sometimes it's important. You know, so like, for example, if I write something like this, first of all, what's the answer?
1.
1, right? And so what am I talking about here? Am I talking about a symbol or am I talking about a string? Well, I don't know. We haven't talked about lengths of symbols, right? So I'm probably talking about a string, right? So if I'm finding the length of something, I'm probably talking about a string. So A can be a symbol, A can be a string. And, you know, it flows naturally from one to the other, so it's usually not going to be a big problem. But just be aware of the fact that there's some overloading, some ambiguity going on there. And so to that end, you know, can you come up with a theorem? First theorem, we're not going to bother trying to prove, but if what would be a way of expressing the length of the string WX? Yeah.
The length of W plus the length of X?
Sure. Right. Just putting things together, no big surprise here. All right. Okay, prefix. We don't have notation that we can really use for this yet, but we can talk about the prefix of a string. So in fact, let's come up with a concrete stream. Give me an example of a prefix of ABB. A is a prefix of ABB, yeah. How about another one? AB. Okay, those are the two most obvious. There's one that you may feel is controversial. What would be the controversial one? Yeah? No, that's not controversial. Say it again. ABB. And why would that be controversial?
There's no postfix.
You know, because it's the whole string, right? So there's another adjective that we would put in front of prefix to preclude ABB. Maybe that was just way too complicated of a question. I'm looking for an adjective to put in front of prefix so that it's the prefixes that don't include ABB. And it's the same prefix you use like in sets for the same kind of situation. Yeah.
Is it exclusive prefix?
No. Okay, hang on. Like what is a subset of a set that's not the entire set? Right? If you have a set that's a subset that's not the entire set. It's not just a subset, but it's a
Strictly.
proper subset. Right, there it is. So ABB is a prefix, but it's not a proper prefix, okay? So we just reuse that term. And then finally, as a possible prefix, someone suggested lambda. What do you think?
Yes.
Is lambda a prefix? Yeah. And actually, you can sort of define a prefix as, and maybe we actually should have done that. Well, yeah. So how would you define a prefix? What is a prefix of W? Yeah, no, but I want a general definition that includes all four of those in one fell swoop. So let me get you started. Prefix of W is a string X, and I'll even help you some more, where, so what kind of X is a prefix of W? All right.
I'll give you the first part, where
The first part.
it begins with the very first symbol. That I don't know how I would phrase the rest of it, but that includes the other symbols in order.
Yeah. You're avoiding, like, I may have led you a little bit astray. Let me just make sure. We're flying through this so fast, I forget what I said and what I haven't said. Did I use a word here?
Concatenate.
I did. Okay, so we have concatenate, right? Okay, so we have that word. So my hint is then, let's if you're going to do it in English, maybe you can describe a prefix in terms of a concatenation. That might help. Yeah.
Okay, my definition doesn't use concatenation, but I was going to say where X is followed by some set of symbols.
Yeah, and you don't mean a set of symbols. What do you really mean? You don't mean a set of symbols. You mean something else.
String of
Yeah, a word or a
symbols.
string, right? So let me help you a little bit. Prefix of W is a string X where you're talking about this other string where, so there is another string, and I usually don't write this much, but somehow Z, and now we're almost home free, right?
That follows X.
Yeah. Now let's use concatenation. Yeah.
How about X concatenated with Z equals W?
Right. where W equals XZ. So that's where the prefix is. So why would ABB be a prefix of ABB? Yeah,
Because in this case, X would be ABB and Z would be lambda.
and Z would be lambda, right? Yeah. So ABB is a perfectly good prefix because Z is lambda, right? And why is lambda a perfectly good prefix? Then this sort of kind of, this definition sort of makes it all clear. So why is lambda a perfectly good prefix? Well, you might as well finish the thought, sure.
Because then X is lambda and Z is ABB.
Then X is lambda and Z is ABB. Right. So anytime you can find an X and a Z, put them together, then you've got a prefix. So that's all there is to it. Yes?
Is there a case where we can concatenate multiple lambdas, or is that just?
Yes. And well, actually, let's have another theorem. If I concatenate lambda with lambda, and sometimes I use a dot for emphasis, just to make it super clear that I'm concatenating. Usually we don't have to, right? In fact, is this the first time I've done it?
Mhm.
Yeah, I guess it is. So sometimes just for emphasis, just to remind you I'm concatenating, I put a dot there. And so in other words, I don't have to put a dot there. I could just say lambda, lambda, and concatenate them together. But who can give me another way of writing that? Okay, hang on. Give me another way of writing that. Yeah?
Lambda squared.
Yeah. Okay. So what you've done is you've jumped ahead to something else I was going to talk about. Oh, no, we did talk about it here, right? Which we talked about here. Never mind. So I'll take lambda squared. But I don't think we're done. Hang on. Okay, hint. Raise your hand when you know. Can't we simplify this a little? Yeah? Yeah, lambda. The empty string followed by the empty string. Just the empty string, right? So you can concatenate as many lambdas as you want. And you'll just always end up with lambda, which is what the question was, right? Okay. Okay, in the effort of sort of picking up the pace a little bit, if I were to change prefix to suffix, then what? Well, let's first of all, so this is prefix, just to make completely sure. What are the suffixes of ABB?
B.
Lambda, okay. Then I heard B,
BB.
BB,
ABA.
ABB. Right.
Oh.
Oops. Yeah, really. That's right. And what changes down here?
The order.
Yes. Switch X and Z.
Such that does.
Oh, switch them here.
Yeah, especially there. Or switch the
Yeah.
Or
Yeah.
switch terms.
Just don't do both.
Just don't.
Don't you both? Well, I oh, yeah, switch these two. Yeah, either switch these two or, I like to stay alphabetical, so I'm tempted to switch these. You don't like that, huh? But anyway, that's the idea, right? So if you can put something in front of it and get the string, then it's a suffix. So we have prefixes, we have suffixes. We have concatenations. Yeah, I guess that's okay. Okay. What do you think this is? I mean, you probably know. So, that was a comment. Yeah. So, what do you? So, what we're doing is this is another operation on a string, right? So for example, I guess it's probably better just to do an example. So the secret is to figure out what R means. So what does R mean?
It means we're going reverse order.
Yeah, R for reverse, right? So that's what R means here. So therefore, ABB reverse is BBA. Correct. Okay, so that's just another operation we do. Well, okay, so what's the definition of reverse? If you were to define it, I just gave an example. If you were to define it, how would you define it? Yeah, it's not easy, right? I mean, in a way, I kind of agree. You have to somehow talk about the symbols, and you have to talk about the way the symbols are written, and you have to talk about reversing them, right? Which does not sound easy. So it turns out we have a really elegant way of defining it, which has tons of advantages, which I'm sure you'll appreciate too. And that is, we'll define it recursively. So, I mean, among the many advantages of doing it recursively, beyond the fact that we all love to do things recursively, is the fact that it allows us to prove things about reverse and stuff, because we'll have this nice formal definition. And that reminds me, and then from your 256 days, if you have a definition that's recursive and you want to prove something about a recursive object, what does the proof almost always look like? What kind of proof do you use on a recursive structure or a recursive object to prove something about it? There's a particular proof type. Say it again.
Induction.
Induction,
Yeah.
right? You almost always use proofs by induction. So we'll have not only will we now have a simple definition for what reverse is, but then we'll have a simple way of proving things about it. Because proofs by induction are always simple, right? Okay.
Yes.
Yes, thank you. So how do we if we're going to define it recursively, we have to somehow talk about a big string and a smaller string, right? So where do we begin? So I mean, W is this string, but we need to be able to talk about,
The length of it.
yeah. Well,
Can we do?
no. Not if it's recursive. And that's what makes it a little bit tricky. So here's the hint, and in fact, let me just spell it out so we can keep things moving, and also give you another sort of rule with this class. Well, no, okay, so W is some big old string. And I want to talk about this big old string in terms of, and what's a string made out of? Again, one more time.
Symbols.
Symbols, right? So if we're going to do this recursively then, we want to talk about a smaller string, and we want to talk about a symbol, its basic component, right? So therefore, how do I want to think about W? I want to think about it in terms of a symbol and smaller string. So what does W look like? Yeah?
So the first, I guess, non-empty symbol is going to be the prefix of the word, and the rest will be.
Yeah, so it's got a prefix. That's true. Right, yeah.
W can't just be like an array of things, of characters? Or?
It can, but now it's not sounding recursive anymore. That's sounding more iterative. You're visualizing it in an array. And just as a side point, that's sounding too implementation dependent. I just want to think about a string a little bit more abstractly. So yeah, we don't want to. That's what we're trying to get away from, visualizing it as a list of symbols. I want to think about it recursively in terms of smaller strings and symbols. Yeah.
So I might be getting ahead of you, but like you think of it as like a hamburger, like two buns and everything else inside, right? You flip the bun and then move it.
You are getting ahead of me, and that is not really recursive, because what's inside the bun is different than the bun. And so if it's recursive, it'd be more like a loaf of bread, where they're all the same piece. So,
Better now.
yeah.
Would it be the prefix concatenated with the string minus the prefix?
And what would the string minus the prefix be?
A new string?
Yeah, but it's more than that, really, right? Yeah. Last chance.
Let W be a symbol concatenated with a proper prefix.
Yeah, only you said it backwards, because you don't want to put something in front of the prefix, right?
Oh, yeah.
Right, you want to put it after. So the way to visualize it is, a string W is a smaller string followed by a symbol. Okay? That's sort of a recursive view of a string. A recursive view of a string is a string followed by a symbol. Let's see, we got one here that ends in A anywhere? Well, here, like ABA. What is ABA? ABA is the string AB followed by A. Right? Now, technically, if we're going to be general, W can either be that, or, of course, it could end in B. Right? So that means anytime we're going to talk about this stuff recursively, anytime we do this induction stuff, we're going to have two cases, right? We're going to have the case where the string ends in an A, and we're going to have the case where the string ends in a B. But if you think about it, fundamentally, structurally, is there any difference between this case and this case? No. We're just viewing everything except for the last symbol and then the last symbol. So what I will be doing in this class sometimes, and so you're going to have to be prepared for this, is sometimes I will write XA to mean the string X followed by the letter A, but sometimes I'll be treating A as a variable. I'll just be saying it's the string X followed by some symbol, which I'm calling A, but might be a B also. It might be an A or it might be a B. Because anything I say with A, I can also say with B. So why say it twice? So it's your job to sort of recognize whether it's really an A or whether it's a variable. And if you're not sure, then ask me, okay? So just make sure, When I write an A down, and you're suspicious, say, is that really an A or is that a variable, okay?
Because something from the middle of the alphabet?
Most letters are taken,
Okay.
Letters near the middle of the alphabet tend to be integers. Letters at the end of the alphabet are strings,
Okay.
and
Okay.
it's kind of hard.
Can I
So,
buy you,
what's that?
Can I buy you different colored markers?
Yeah. That would work, I suppose. So in terms of definition then, what is WR reverse? In other words, what is XA reverse? What do you think a good definition would be? Okay, hang on. Okay, go ahead.
About AX reverse?
Yeah. So there's a nice recursive definition of reverse. Take the last symbol, move it to the front, and then reverse everything else. And then reverse everything else, right? That's recursive. But you're reversing a smaller string. So all is good. Right?
Right, yeah.
But this definition is flawed for all you experts in recursion and induction, right? So you know the flaw? This is a yes or no question.
You need to have a.
That's a yes or no question. So what is the flaw? Yes.
It never ends.
You said that? Yeah. Yeah, it never ends. Why doesn't it end? Because we're missing. So let's hear it from that side of the room. Or did we already spit it out? I think we did. We're missing the base case, right? The base case is what allows recursive definitions to end. I hate wording it that way, but as you well know, but we'll live with it for now, all right? So what is the base case? Or cases?
Where X is equal to alpha or lambda?
Yeah, that's a fine base case. I like that one. So I'm being a little lazy here. I'm not talking about lengths or anything here, but we're all friends here. We can do that.
We need the lengths.
Yeah, that's all right. So what I've left out here is, so in other words, if W has length greater than or equal to 1, then this is the definition, because the length is greater than or equal to 1, so I have a symbol to peel off the end, right? And then the base case is that. Lambda reversed is obviously lambda. And let's check. Let's check if this definition is doing what we think it's doing, or what we want it to do. So according to the definition, what is A, B, B, reverse? What does the definition say that that is? And don't say BBA, right? Just what?
BBR, B parentheses, ABR.
Correct. Correct. Well, okay, slow down. Whoa. Let me get this one in. Right. That's what the definition says, right? So here's this is W, so I've written it as an XA. My A is B. Sorry about that. So I take that last symbol, move it to the beginning, and then I have to reverse the rest of the string, right? So then according to the definition, what is this?
BBA super R.
Right? B, do you want parentheses around it?
Yes.
No.
Why don't you go no?
Yeah, I
It's
think I
uniform.
do.
Okay.
I don't think I can stay. Yeah, we were scoring so good.
Yeah. Life's tough. Okay.
Just the little things.
Now what?
Yeah. BB lambda.
Or just,
Say that again. BBA lambda.
super R.
Why?
you just.
Because it's in the definition.
Where?
Oh, well, okay. But it's the base case. We need to see the base case.
Exactly. We need to see the base case. To see the base case, we need to see lambda. I don't even see a lambda yet.
Yeah.
Say that again. A, B, B, lambda. Oh, you want to put a lambda at the end of this?
No. Just the next one, if we're forming A off of an A, we're just gonna end up with that.
Right. Why do we know that?
Because that's the.
Right. But so, yeah, I have two choices, to apply the base case or to apply this rule. And right now, I don't seem to be able to apply either of those rules.
That's fine. You're just looking for
Yeah, because you can.
a prefix.
Right.
And then we say it is.
Well, so I mean, so do I have an XA? I don't have an XA here, I just have an A.
Yeah.
And I don't have a lambda there because it's an A. So I need,
We need one more.
we need to slow down here a little, right? That's all I'm saying, yeah?
You do have a lambda though by definition of prefix or suffix.
Right.
Yeah.
So let's rewrite it one more time to convince me.
BB.
Oh, okay.
BB, lambda, no. A and lambda.
So that's the question. Do I want A lambda or do I want lambda A?
Lambda A.
Lambda A, right? Because I'm
Yeah.
taking the symbol off the end and moving it around, right? Now we're good again, right? Now I have a string X and a symbol A. Now that I have a string X and a symbol A, so now what do I get?
BBA lambda super R.
BBA lambda reverse. Then what do I get?
The base case on the lambda.
The base case on the lambda,
BBA.
BBA, lambda, and what do I get?
BBA.
BBA.
Mm.
So sure enough, the recursive definition really is doing what we want, so that's nice, yes.
Okay. Do we have any concerns that there is a lambda before and after A?
We do not.
Why is that?
Well, because as someone very eloquently put earlier, I think we have lambdas everywhere, right?
So we just pick and choose lambdas?
Exactly. If we need one, we just pop it in there, right? Because, you know, we got an arbitrary number of lambdas wherever you want to put them, right? So we just, I mean, and you put it very well, pick and choose, you know, stick them in there if you need them.
Okay.
Okay, so the recursive definition is doing what we want, that's nice.
That was crazy.
Things you can do with strings, you can also do with languages. So, generally speaking, any operation you do with a string, you can do with a language. Well, let's head over here. So, for example, what do you think the reverse of a language is? And let's get a concrete case again here. So let's have. Well, here we got a lot of concrete cases here. Well, no, none of them I like. What do you think the reverse of L4 is? So let's do that. You know, how would you generalize it to a language? Okay, hang on.
You can't, right? Because there's no order.
Yeah, so the gut reaction is you reverse the obvious thing, right? So instead of AB, ABB, and lambda, make it lambda, ABB, and AB, right? But if you're reversing the elements in the set, what did you say?
There's no order.
Yeah, it does, that you haven't done anything, right? So that means reverse would never do anything. So that's probably not what we want to do. So what do we want to do? Okay, hang on,
Okay.
hang on. What do we probably want to do?
Can't go any answer there.
Concatenate?
Concatenate all the elements.
Well, but the crucial operation here is reverse, right?
Reverse each.
Yeah, what was there a hanging out there somewhere? Okay, go ahead.
Oh, just reverse each word inside of the language.
Right, reverse all the words inside the language. So the reverse of this language is the reverse of the individual words. So in general then, how would you sort of describe that somewhat more abstractly? Say again?
Redistributing the report.
Right. So with 256 set notation. So it's the set of all, well, there's two ways of writing it. Well, let me just write it the two ways and see which way you like. Well, you go ahead, let me hear
I
yours.
was gonna say it's, the words where if the word is in the language L, then reverse that word.
Right. And so the way you would write that is with set notation, you would say, okay, reverse that word. Which word are you reversing? The words in L. That's kind of what you said. Right? That's sort of the constructive way of doing it. You know, take all the words and reverse them. There's kind of an algorithmic way of doing it too. The algorithmic way of writing it is say, okay, I want the set of all words, and then what property does this word have to have if I want it to be in this language? It has to have the property that its reverse is in L. Right? So the first one sort of constructs them, takes the words and reverses them and throws them in there. The second one's kind of an algorithm. Which ones do you like? Well, you like words that, when reversed, happen to be in L. Looking at your faces, I think you like the first one better. Huh? But they're both perfectly fine, right? Yes.
How would the reversed ones be in the original? Oh, wait.
Yeah.
Ah, okay. I get it. Never mind.
Yeah, you have to think about it. I agree. It's good.
Because the operation is being done after it's agreed that it's an element of L.
Yeah. Okay. Okay, L5 equals ABB L6 warning, I'm intentionally trying to trick you here. Okay. So L5 and L6 are those two. Like I said, anything you can do with strings, you can almost always do with languages. What do you think the concatenation of these two languages are? And see, here I'll use the dot just for emphasis. Okay, hang on. So you sort of know kind of what the rule is. When we extend something to the language, we sort of do it element by element, right? That's what reverse was. You knew what to do with the string, so you do it with all the strings in the language. But with concatenation, that sounds a little more complicated, right? Okay, hang on. All right, is there a question there or an answer? Okay, so hang on. So, well, what will it mean to concatenate two languages? Yeah?
Just take one string from one language, concatenate the strings from another language, then
Right. Yeah. So, okay, let me ask you a different question, because it sounds like you said the right thing. And I was trying to trick you here. So let me see if we're all on board here. What is the cardinality of that concatenation? 4, right? I tried to trick you into thinking it was 2, right? I was trying to trick you into, okay, concatenate these two elements and then concatenate these two elements, right? And that's not what you do. You concatenate every possible pair. Okay? So indeed it is 4. And so what do we get? You know, we get A, B, 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 A, B, A, B, oops, not B, 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 and B, B, A. And so the definition was, so what is the definition? Well, it has that feeling, right? It's kind of like a cross product, right? Because you're doing every single possible pair, right? So, you know, well, let's use L1 and L2 again, since we're on a different board. Right? So you're getting every possible element out of L1 and every possible element out of L2. So it's a set of all Wx such that
W is a number of L1 and L, what is it? And X is a
right.
number of
right.
2.
Yeah, that's it. That's what L1, L2 is. Yes?
And if you end up with a repeated element, you just list it once, right?
Because it's a set. Which means you've answered you've already answered my next question. Is this theorem true? And I just heard a no, well, because that's why you asked the question. And this is sort of good practice. So if you think a theorem isn't true, again, in 256, if someone said something might be true and you didn't think so, what was sort of the one word? Yeah, that's the one word. You need to provide a counterexample, right? So can you provide a counterexample where this is not true? Yeah.
one of the languages only have lambda. Would that be?
Only lambda?
If they don't have the same number of elements?
Well, no, I mean, it's true a lot of the time. I mean, for example, you know, if this is A and A, and this is B and B squared and B cubed, certainly there's 6 elements in this concatenation, right? You know, AB squared, AB cubed, A squared B, and so on, right? So that's not where the problem is.
Yes, his hands up.
Yeah, I know, but I'm
Okay.
ignoring him.
If there's an element.
What's that?
If there's an element that's in both of them, would it be double counted?
Not necessarily. Again, if I have, just again for simple, if I have an A and a B here, and an A and a B here, these sets are identical in fact.
Yeah.
But the concatenation still has 4 elements, right? So that's not where it happens either. So he gave the hints away earlier when he asked that first question. What happens if the same element appears twice? So is there a way to concatenate these two sets so that you get the same element twice? Okay.
Okay, well, let's say we have one set that's B and BB.
That'll work.
And then let's say the second set is BA and A.
Oh, well. I liked your idea, so I just ran with it.
It would work, it just.
I know. It's keep life simple here. So what is this concatenation?
BB.
So the smallest string is BB, and then BBB. And the point is, we see BBB twice, right?
Yeah.
BBB and BBB. And then we also have B to the 4th. So it's not the product, it's one less, right? So the concatenation doesn't always give you completely different elements. There was one more thing we wanted to, I guess that's good enough. Okay, so most of this is in the book. I just gave maybe a little more padding. We'll pick up where we left off. Read the book. If you have questions, I use Canvas. I follow Canvas. Discussion groups and stuff are fine. I usually follow along, so feel free to do that. Homework, maybe next time.
This is